Thank you again for the invitation. Sorry, with the difference in times, almost 12 hours, it's difficult for me to be with you during some of the lectures. And it is now we're starting 10 minutes late. So how much time do I have, Kostas, before I start? I'm assuming I have.
It's 1 hour. It's 1 hour. You have 1 hour.
1 hour. Okay. All right. So, okay. Well, maybe I will finish earlier. We'll see. Okay. So I'm going to talk about the new blow-up criterion for the 3D Euler equations. And it's mostly computation study. I will show some of the analysis and then try to support it by computation study. So here's disclaimer. We don't claim, we're not, I'm not a computational person, and my collaborators, some of them are computational people, but we don't claim that we have like definite singularity or blow up or non-blow up. Nonetheless, it is a new criterion that has been around, but people in this computation community have not been testing it. So we decided to do it ourselves and to maybe to intrigue or in some sense to excite or to some people to try to compute with this thing. So here's the outline. So we're going to talk about the Voigt model. This is our initiative. Then I'm going to talk about convergence of the Voigt model as some parameter goes to 0 to Euler and develop a blow-up criterion for the blow-up of Euler equation. I will demonstrate the same phenomena for Burger's equation. So the regularization will be like the BBM, Benjamin Bona-Mahoney equation. And then I'm going to talk a little bit also about similar criteria, which happens for MHD and for the Boussinesq equation. So here is the Navier-Stokes equation. We should probably have seen it a lot during this conference. So this is the equation of conservation of momentum. Incompressibility, the unknown are the velocity vector field and the pressure. And nu positive is the kinematic viscosity. As we know about Euler equation is since the work of Leray, in 2D dimension, is there singularity developed? Of course, we know that the answer is no for the 2D, and for 3-dimensional equation, this is 3-dimensional case. This is still one of the open problems, one of the Millennium Clay Prize problems. So about whether singularity developed in finite time. So what happens if the viscosity equals to 0 in 3D? There is some recent progress. I will mention it briefly here. The recent progress was, in some sense, different than the situation I'm talking about. It is mostly related to axisymmetric fluid. The first result was by El-Guindi, and then there was some result joined by El-Guindi joined with Masmoudi and Rahul, in which they look for axisymmetric without swirl, and they have shown that the Euler equation develops singularity in finite time. But for initial data and in the space C1 alpha, when alpha is very small. Now, this is a nice result, and this is in some sense kosher. This is a valid result because the classical result in 3D Euler for short time well positiveness is due to Liechtenstein, in which she basically proved that if the initial data is in the space C1 alpha, when alpha positive, then for short time you have existence, uniqueness, and continuous dependence on initial data in this space C1 alpha, when alpha is positive. So these people have shown that for axisymmetric flow, without swirl, okay, without swirl, if the initial data is C1 alpha and alpha is small, it has singularity. The result, they cannot show it into large alpha, namely for initial data more regular. And I can tell you in some sense why. The reason is if you look for the axisymmetric Euler equation, then there is a quantity which is invariant when you have no swirl, axisymmetric no swirl, and the quantity is omega over r. Omega r is conserved for classical solutions. Therefore, near the axis, if omega over r is in L infinity, then near the axis, if it is bounded, then when r goes to 0, omega must go to 0 because omega over r goes to 0. Therefore, if omega at the axis is 0, then omega over r is, in some sense, should be a Lipschitz function near the axis. So omega is Lipschitz, means the function u, morally speaking, should be C11. Now, for this space of, for this particular space, one can prove global existence and uniqueness for axisymmetric without swirl. Namely, If the initial data where the omega over r is in L infinity, namely when you are like C11, then one can show short global existence and unique symmetric flows. And therefore, this result of El-Guindi and others cannot be pushed there because we have global existence for alpha large. Just to give you an idea about what's happening. Now, the other recent development is a new result by Tom Howe and company, which is computer-assisted proof. I must confess, I didn't have chance to follow all the details there. I listened to Tom Howe, and it's a computer-assisted proof, yet still to be, the verdict still out there to be confirmed that indeed people can see a finite time singularity in Euler equation. So this is some of the recent, but then all the work is more on axisymmetric, but nonetheless, it's okay. In my case, I'm going to talk about more classical scenario where the singularity is not driven by the boundary, probably driven intrinsically by the structure of the nonlinearity. Okay, let's continue with my talk. So this red thing here that I mentioned is about recent progress. I made a couple of comments. So to summarize, axisymmetric without swirl for C1 alpha, alpha small, El-Guindi, and then later El-Guindi, Masmoudi, and Rahul proved blow up. But as I said, these flows should not have singularity.
Sorry, excuse me, Edriss, we see just the first page of your slides.
I know. I didn't change. I'm just basically summarizing. Yeah, so thank you. I'm summarizing what I said earlier.
People wanted to check. Thank you.
Okay, yeah, very good. Thank you. So what I said is, again, summarize that the result in the axisymmetric without swirl, the blow-up is in C1 alpha, but we know that if the solution is smoother than that, C1 alpha, alpha large, basically alpha bigger than 1, so then we have global regularity for those flows, and I explained to you what's the situation. So therefore, this result, in some sense, does not treat the what is a, let's say, physically relevant situation when omega over r is invariant. And the other result, which is of Tom Howe, which is singularity driven by the boundary somehow, and this is all basically not really, there's near the axis now that what he sees, and this is another result, which is the paper is out there to be checked. Okay, so now what are the search for? There was a long time for search for singularity. The classical similar work is Bill Cato Maida in 1984, which says if the vorticity is the integral in L infinity, finite if and only the solution is regular of Euler equation in zero alpha. Now there are analytical blow-up criteria. I'm just basically mentioning some of them. Bill Cato Maida, there's one by Bonse. Bonse is basically, he looked into the case when you look to the gradient of U, omega is the antisymmetric part of the Jacobi matrix of U. So he looked for what happens if the symmetric part. So he had similar criteria concerning the symmetric part. Then there is some result of Ferrari, which is like Bill Cato Maida embodied domain. Then some result of Konstantin Konstantin Maida, and many other. There's some by Larius and myself and Cha. There is Gibbon and myself, and there's Cheskidov and Schvidkoy. There are many, many results about different criteria for blow-up. Now, computational search for a blow-up, this is a very long history, and I'm sure among the audience there is expert in that. It started from the old work of Morf, Ortzak, and Frisch, 1980, then Brachet, Myron, Ortzak, Nickel, Morf, and Frisch, 1983, and so on and so forth. The list is very long about basically trying to find singularity, and sometimes the answer is yes, yes, no, yes, yes, no, no, yes, yes, no. And now, as we say, there is this kind of like computer-assisted proof by Tom Howe, which is still to be checked. But the most relevant result in which basically one sincerely is Liu and Howe, 2014 and 2019 about the computational. And the result at that case, it is basically axisymmetric, but they see the singularity near the boundary. The new result of Tom Howe is not really singularity of that type. Okay, now, how can we basically, in some sense, control the disobedient gradient? So there were many attempts to regularize Euler equation. I mean, the first one, even Navier-Stokes, by Lyons, in which he considered hyperviscosity, 1 plus epsilon. Epsilon is not small. You have to take the right epsilon. The total power is basically epsilon is 1/4. If epsilon is 1/4, you have existence and uniqueness for the Navier-Stokes and for the Euler equation. Another attempt to regularize Navier-Stokes and Euler equation is by having nonlinear viscosity. And this is like motivated by a turbulence model by Smogorinsky, and then Ladajensky analytically investigated that, in which you look when you have here a function of the gradient, which is like gradient of U absolute value to some power, without getting into the details of the power. If this is large enough, then one can control and one can show that you have global existing uniqueness of the Navier-Stokes equation. Now, similarly, Leray, basically you can regularize the transport by taking U convolution with some kernel. You get some U epsilon, then one can really show regularity. So there are many attempts to investigate the Navier-Stokes and to regularize it. Mostly it's more adding extra viscosity, linear or nonlinear, and then many other attempts. It's just putting things in perspective. Now, I'm going to talk here about the Voigt model. And the Voigt model is basically taking the Navier-Stokes equation as is and adding this particular term. Now, where we got this term, when we worked a lot about the alpha models of turbulence, we made many variants, and suddenly we discovered this particular regularization, in which we later discovered that it was introduced by other people, by Voigt, in the context of viscoelastic fluid, not as Navier-Stokes equation, but it is a model on its own. Yet one can really think about this term when alpha is very small, when alpha goes to 0. Formally, I get the Navier-Stokes. So one can consider this as a regularization of the Navier-Stokes equation when alpha is positive. And of course, you have the incompressibility. Now, when the viscosity equals to 0, then this term is disappear. One can show that this quantity, namely the L2 norm, usually for Euler, it is invariant or conserved. But now you have this extra term, which is like a penalty, if you want, alpha square graded phi square coming from this term, which makes the sum of these two quantities is invariant. So for the Euler, for the Voigt equation, you have this extra term. Indeed, when alpha equals 0 formally, you get the energy is converted if you have classical solution. This is just to motivate what is the contribution of this particular term. So what are some properties of 3D Euler Voigt model? So this is first studied with a viscous case by Skolkov in 1973. Skolkov was a student of Ladajensky as a model for polymeric fluid when the viscosity bigger than 0, and he proved global existence and uniqueness. Now observe that if you look to the steady state, namely when you drop this term, the time derivative, the steady state for the Euler-Voigt and for the Voigt model and for the Navier-Stokes are exactly the same. So this is interesting because in some sense, if you look for infinite time average, like you trying to look for statistical solutions or infinite time average, the time derivative term disappears and you get the Reynolds equation. Therefore, the Reynolds equation for the Voigt model and the Reynolds equation for the Euler equation, for the Navier-Stokes equation are the same. Yet the dynamics is different, but the Reynolds equation are the same. So this is an interesting observation. And in previous lecture, in one of those conferences, I gave a lecture about the statistical solutions for the Voigt model. And I will not going to repeat it now, but this is observation, which is important and good to keep in mind that the steady state are the same and the Reynolds equation, the average equation are the same. Now, what's interesting about this equation is that the regularization inviscid is not viscous. Namely, without viscosity, you have a new invariant quantity, constant quantity. So there is nothing damped if you have no viscosity. So in the Euler case, namely when the viscosity equal to 0, this is regularizing the equation seemingly. I will tell you in what sense it regularizes the equation, but without really adding hyperviscosity as it's done like by Lyons or by Smogorinsky or Ladajensky. Now, what happens is we proved global regularity in bounded domains. This is a result for viscous case by Yamping, Cao, Lens, and myself. And then we proved that the solution global electric regularity in periodic case, again by my collaborators and myself. So we show that the solution analytic in periodic, namely they become analytic solution. Now notice that in the viscous case, although the parabolic characteristic of the equation destroyed, why so? Why destroyed? If I forget about the nonlinearity, then you have here Laplacian on U and Laplacian on U. Laplacian cancel. The equation looks more or less like an ODE. It is not a heat equation type because you have time derivative of the Laplacian. So the equation is no longer parabolic. Therefore, I'm not seeing immediately smoothing effect in the dynamics of this equation. So all of the parabolic character of this equation destroyed. So this equation still has a global attractor, and the attractor, the solution attractor, are much smoother. Why? Because even though the initial data could be rough, it remains as rough as the initial data, the solution. However, when time goes to infinity, because of this damping, the roughness seemingly disappears, and this is a result that we have proven with Kalantara. Now, so the solution does not experience any instantaneous smoothing. That's exactly what I mentioned, because the equation is not parabolic anymore. So, as I said, it is recovered at the long-time behavior at the attractor, and therefore, if you are interested in turbulence, which is not about transient but about long-time behavior or statistical solution, then in some sense this model could be, in some sense, one can see that this model, even with the alpha, has a dissipation length scale. And in fact, one can show that exponential decay after a certain number, depending on alpha and on the viscosity. But again, this is not the topic of my lecture. I just basically put it in perspective because this is a workshop about turbulence. So therefore, this equation still see the dissipation length scale or dissipation phenomena, namely dissipation range, even though it is inviscid. It is kind of like, it's not parabolic in type as we see it in the Navier-Stokes equation. Now, suitable weak solutions with Navier-Stokes when alpha goes to 0 has been proven by Berselli, Spirito in 2016 and 17 by suitable weak solutions in sense of Caffarelli-Cohn and Nirenberg. So one can show that in the Navier-Stokes equation when alpha goes to 0, the suitable weak solution for this model converge to the ones a la Caffarelli-Cohn and Nirenberg. This is the history about the Voigt model. Now, doing some computations here. Okay, I'm trying to get this. So this is like Euler, namely no viscosity of the void at the resolution 1024 cube. So alpha square gradient plus u square, it's equals to that. We have shown that this is invariant. In fact, we can show that the Euler alpha is globally well posed. I mentioned that earlier by result. I have seen this earlier here with Lunasen, and yeah, basically we are shown even without viscosity you have global existence for this model, and therefore this quantity is invariant. So one can show, therefore, that this quantity is invariant. So initially it is given by this value, and at later time it's equal by this value. So let us look into track this quantity and the L2 norm, the sum of them. The sum of them is constant. This is in the simulation. This is the sum. But now, if you look to the L2 norm, you can see this is for different values of alpha. So when we go up, the alphas are decreasing. Okay. So therefore, this is the gradient. You can see when you evolve in time, the energy is decreasing, but the gradient is, in some sense, is increasing. And this is like the crosses is the intersection point. So this is a simulation for different values of alpha. So you can see, in some sense, that when you evolve in time, because this quantity is constant for this model, the energy is decreasing and it's compensated by enhancing, or the gradient is getting larger and larger. So now this is the picture of the Euler void, the vorticity at the time equals t equals to 2. And if you go for further time at t equals to 6, you can see that you have really a lot of structure in the Voigt model, in some sense for the alpha at the relevant alpha that we have at hand, and therefore it is really trying to mimic what we see usually in turbulence. So coming back to remind you of what the analytic study that I just mentioned earlier. Okay, so the analytic study, as I mentioned earlier, you have, this is the equation. So as I say, global existence with viscosity equals to 0 or positive of the Navier-Stokes void, you have global existence and the space H1. And if the viscosity is positive and then under homogeneous or Dirichlet boundary condition, you have global existence as well. Oops. And now one can show also when the viscosity is equal to 0, if you are in the space HS, so in the space HS, you also remain in the space HS. In other words, that you have a global well posedness in the right spaces starting from the space H1. Now I'm going to look about convergence as alpha goes to 0 and to deduce from that blow-up result. So what happens is the following. So as I said, oops, this is the analytic results. So the convergence, given initial data in the space HS, S bigger than 3. Namely, you need initial data to be smooth enough. And let U be the solution of Euler equation with this initial data. We know, basically, for such initial data, you have short-time existence and uniqueness. Now, let U alpha be the solution of Euler void with the same initial data. Now, this equation, U alpha, has a global existence. Now, here's the result. Convergence. If U is solution of Euler in the interval 0t in the subspace HS when S bigger than 3 half, and X bigger than 3, then U alpha, the solution of Euler void, converging to U in L infinity in time with values in L2 in space. In other words, the solution of Euler void converges to the solution of Euler in the interval of existence of Euler equation. All right, what specifically we have? We can show that, in fact, the L2 norm of U alpha minus U plus alpha square, the gradient of U alpha square, this is gradient different, is less than C alpha square e to the CT minus 1. In other words, the supremum on the interval 0t of the existence of Euler, the supremum of the L2 norm less than constant times alpha. Particularly as alpha goes to 0, we have the rate of decay or the rate of convergence, which is like alpha. We're going to capitalize on this fact in a minute to conclude something. So I summarize, if solution of Euler exists in the interval 0t, the Euler alpha, the void model, the void alpha is converging to the solution of Euler, and in fact we have the rate of convergence like CR. Now here is the first criterion, which is a naive criterion. We know that for the void model, the energy is conserved, and now by the energy means the sum of these quantities. Now, if I take in the interval of existence alpha go to 0, I know that this norm should converge to this norm by the previous result. Now, I don't know if this is converging, so I can take the lim sup of this. Now, I take the limit of this equals to 0, and therefore I will have to have equality here. Okay, so what happens is the following, that we have a new criteria, and the new criterion basically tells me the following, that if I take the lim sup of the left-hand side, it's equal to the lim sup of the right-hand side. The left-hand side, this is converging, this is the lim sup of this quantity, and this is decaying because this is constant, here is initial data. I have this equality. So what happens? We have a criteria now. This is as long as the solution of Euler exists. Otherwise, I don't have this convergence at this part. So suppose there exists a finite time t star such that the lim sup as alpha square, so namely this quantity, and the supremum, because this is true for every time t, the supremum in the interval 0t star is positive. Then the 3D Euler must develop singularity in the interval 0t star. Why? Because I know that if I don't have singularity in Euler, then the energy is conserved. So this term should be equal to this term. So this term should be 0 at every moment. In particular, the supremum should be 0. Aha. But if this is positive, when I take supremum in time, this is positive, then therefore I couldn't have had a regular solution of Euler in this interval. So the criteria is merely on the void model, nothing about Euler. The only thing they share together is the initial value. I take initial value and then I simulate void equation, and the void equation has a global existence, and then I track this quantity, the lim sup as alpha goes to 0, and then I take the supremum in time. This is a very naive criteria, but yet I will improve it a little bit in a minute, and this is the criteria that we will use to track the singularity. This is different than the Birka-Tomaida because it is not about the Euler solution, it's about the void solution, which I know exists globally and therefore all the quantities are finite in this case. So what's about the vorticity here, as I said? So the vorticity omega alpha, is basically the same like the L2 norm of this. So this similar blow up criteria has been developed for the surface quasi-isotropic equation by Hueder and myself, and then also for the implicit Boussinesq by Larios, Lonas, and myself. So you have it for Euler, then you can have it for other equations as well. Oops. All right, so the second blow-up criteria, which is a little bit different. In what sense it is different? Here, I take this loop sup in alpha and take the supremum in time. I will do now some other criteria without really going into the details. What happens if you take the supremum in time and then take the lim sup as alpha goes to 0? So suppose there exists a time t star such for this, the supremum of this quantity times alpha, and then the lim sup is positive, then the 3D Euler equation develops singularity in finite time. This is the criteria which is easier to follow, and this is what we will follow here. So moreover, what do we have? Notice the following, that the supremum of this lim is bigger than that. So therefore, this is the first criteria. If this is positive, for sure this is positive, but the converse is not correct. That's why criteria number two is slightly stronger than the first criteria. So this is the quantity I will follow. And to see if this is positive, then I have singularity for Euler. Okay. As I said, the Big-Cato type criteria is concerning omega, which comes from an equation that's not known to be global existence, namely the Euler equation. That's the Big-Cato criteria about the solution that I would like to test if it is under control now. But following the omega alpha, which is the L2 norm of omega alpha, is coming from the 3D Voigt equation, which are globally well posed. So this is in some sense the advantage of this criteria, that the simulation I do is not about something that it becomes singular. It's something which is, I know it is always regular for every positive alpha. Now, comparison with Navier-Stokes, so currently no hope for corresponding well-posedness to not well-posedness for the Euler. I mean, we cannot develop similar criteria for Navier-Stokes in this particular case. I just basically wanted to strictly stress that the criteria we have is about Euler, but not about Navier-Stokes. Oops. So as I said, this is the criteria that we have in mind. Namely, I look at the supremum positive and I take the lim sup as alpha goes to 0. Therefore, the idea is to investigate the behavior of the function f sub t of alpha, which is the gradient of alpha in L2, namely this quantity. I would like to look at its supremum in time and to see how does it behave in alpha when alpha becoming smaller and smaller. So this implication is if the maximum in the interval 0 to of this is bigger than constant alpha to the power p, when p is less than -1, then when I multiply it by alpha and take the limit as alpha goes to 0, I remain positive, therefore I have implies blow up. So if we track this quantity, and if we can show that when alpha is smaller and smaller, it is greater or equal than constant alpha to the power p, p is less or equal than -1, then we have singularity. So how should I say? We are not really, as I said, the disclaimer, we're not really big expert in computation, etc. So we took whatever people have tried before and we followed and to see if really we see some indication. So the numerical method is pseudospectral, i.e. Fourier methods in space. It uses a longicuta of order 4 in time, and we use 2/3 the aliasing, and the spatial resolution is 1024 cube spatial grid, and we use some adaptive delta t respecting the advective CFL condition. So the initial data, we use the usual Taylor-Green vortex, which has been used before, since 1983 and 84 by the earlier work by Brachet, Myron, Ortsack, Nickel, Morf, and Frisch, and in which they indicated, at least at that time, they saw that there is some sort of sign or signature of maybe blowup 4.2. Now, without getting into details whether what's happening there, but there is an indication in some sense that there may be developed singularity for Euler for such initial data. So this is the spectrum of the solution for alpha equals 12 over 1024, and for different times. So when time is evolving, I get the different spectra, and you can see here that the black curve here in the spectrum is t equals 4.2, and then this is the spectrum of the solution that we have for the Euler equation. Now, what happens is the following: is that near alpha equals 16 over 10 to the 1 at time t equals 4.2, we observe that the gradient of u alpha is similar to constant alpha to the power minus 1.1, which is, this is the p, and p is less than minus 1, therefore indication of singularity. And this is what we have seen. So this is the slope of minus 1, and you can see here that basically this is the values of alpha. So in some sense, what happens is that that we see some singularity because of this particular gradient. So that's because the behavior of the gradient is like alpha to the power minus 1. Okay, so this is what I wanted to stress here. So the alpha is decreasing in this direction. So now you can see here that basically you have this indication. Okay, so now what about the 1D analog? This is as much as we're going to talk about the Euler equation. So what about the analog for this equation, the one-dimensional analog? The one-dimensional analog is the Burger's equation, which we know for sure it has a singularity in finite time. So the analog of that is you add this particular term to regularize Burger's equation. So it happens that this is exactly the same type. I put Laplacian u sub t. So this is in a sense a known equation. This is called the BBM, the Benjamin-Bonner-Mahoney equation, which is globally well posed already in 1972. There's nothing much really to show. And in fact, one can show that the H1 norm, namely this norm, the L2 norm plus alpha squared gradient, is invariant. Now, in particular, one can see that if you linearize this equation around the constant state, then the solution of the linearization is of this type. And then one can see, if you take the Fourier, so the Fourier coefficient behaving like that, and the Fourier solutions are exponential e to the power times u to the power, and there times u hat. In some sense, you see the oscillations, which is an indication of dispersion in this particular equation. So this equation is an implicit regularization of Burger's equation. I'm not claiming that when alpha goes to 0, I will converge to a viscous solution or to entropy solution of Burger's, whatever. All what I'm saying, I'm thinking about this as a regularization of Euler. And now, so following the same strategy, one can show, if you look into this particular, one can show, if you look to this, one can show, let me go backwards. So one can show, in fact, that as long as the Burger solution is smooth and nice, then the solution of the Benjamin-Bonner-Mahoney converge into it. And because this energy is conserved, the solution conversion L2 norm, therefore this term should disappear. And therefore, if this term remains positive, as we know, when the shock happens, the gradient becoming bad, okay, then if this is remaining positive, this is an indication there is singularity in the Burger's equation. So that's what we will look at the moment. So we take the Benjamin-Bonner-Mahoney with initial data sign x, and then one can see again So if you look for alpha versus the UX of alpha in this particular situation, one can show that at a certain time that the alpha, the gradient of alpha behaves like a power which is less than minus 1, which is an indication that there is a singularity by this particular criteria. And we know that in this case, we do have singularity because we know that Burger's equation develops a shock in finite time. Okay, so this is another evidence that the criteria is working or the method is working for this particular equation. So this is the situation. Now, let me see, once you understand and once you have some, how should I say it? You have some ideas about this particular, about Euler equation of Burger's equation, one can move to other kind of equation. For example, to the MHD and Boussinesq equation. So if you look to the MHD, B is the magnetic field. So it appears in many contexts, and I'm not going to talk about that here. So here is the MHD equation. And I would like to look for the implicit regularization. So this is the implicit MHD, which we don't know if it has singularity or regularity or anything for this equation. And now I'm going to add the void regularization, namely the implicit regularization. I have the velocity field and the magnetic field. And now the question, where do I add this void? So if I look at this equation with the incompressibility, then I add this particular alpha square in the velocity field and alpha m square and the magnetic field. So one can take one to be 0, the other one not 0. I mean, one can play now the game, which will give you the regularization. So the criteria that we have is the following, that if initial data is in HS and S bigger or equal than 1, then the above system has unique solution globally in time, forward and backwards in time for this particular, with this regularization. This is implicit regularization for the MHD. Now, similarly, if you look to the 2D Boussinesq equation, which is, if you forget alpha equal to 0, this is exactly the 2D Boussinesq system. I'm regularizing the velocity field in inviscid way. So it's not viscous regularization. So global Boussinesq with alpha equal to 0 is still an open question in 2 dimensions. In fact, as I said, some of the work of El-Guindi and the work of Tom Howe is investigating, in some sense, the Boussinesq equation. So there is some progress in that sense. But in general, if alpha equal to 0, we don't know if there is singularity in finite time. So what happens that in this particular case, if alpha is different than 0, so the initial data U0 and theta 0 in HS for S bigger than 1, and if alpha positive, the above system has unique solution which exists globally in time, forward and backwards in time. So this little implicit regularization make the system globally well posed. And now again, one can really check the case of what happens if you have criteria for blow up. Indeed, you look for short time, you have existence and uniqueness for the Boussinesq system, and one can show similarly that if alpha square gradient of U square is remaining positive as alpha goes to 0, then you have singularity in this particular situation. So I think in some sense, this is what I wanted to report to you. It is late for me. It's like almost 11 o'clock at night. And I would like to thank you for your attention, and I'll be very happy to entertain any question.
Thank you very much. Thank you very much. We have time for questions. You see your hand? Yes, I see. Any other questions? Yes. Yeah. So let me ask, start with Rahul.
Can you hear me, Edriss? Rahul here.
Yes, yes, I hear you. Yes, Rahul.
So in the Burger's case, you didn't
Yes.
show us a plot, but suppose you take the alpha going to 0 limit as best you can, then do you see the shock developing, the entropy?
Yes, yes, I didn't show you the picture in the physical space. We followed only the gradient. So let me go back there. So if I go here back to, yeah. So I have shown this is like basically the values of alpha. Okay,
Yes.
so alpha is getting smaller when you go to the left, and this is the gradient. So we have shown, because my emphasis is my criterion. But indeed, it's like basically wherever the shock is happening, this is for different alpha, and this is the maximum of the gradient of U alpha. So you can see that indeed the shock or basically the gradient or the exponent becoming less than -1 just slightly around the time of the shock.
Okay. Thank you.
Hello, hi, Professor Titi. I have probably a naive question. When you are integrating the Euler equation or the Euler-Voigt equation, what kind of time stepping scheme do you use? Does it conserve the energy?
Well, as I said, we use the Runge-Kute order 4, and we tried as much as possible to be, this is basically the summary of what we did, is we use the Runge-Kute in time, 2/3 the aliasing, and we do adaptive delta T respective to affect the CFL condition. So now, now, of course, as I said, we're not really expert in computations, etc. But this kind of like line of work has been laying for a long time, and we couldn't really excite or convince or whatever anybody from the computation community to test it, if it is really working or really just a theoretical work about, or we don't know how to use it or utilize it to show singularity. We said, okay, we do it ourselves. And now the verdict out there. And for this reason, we have the disclaimer at the very beginning. This work appeared in a journal of theoretical and computational fluid dynamics. So people are welcome maybe to try different initial data and try all kind of things and probably see that we don't see what we see, or prove or enhance or enforce our result in some sense.
Uriel, please.
The result,
Hello, this is you.
No, yes, Uriel. Okay, I hear you, but I think the gentleman before you did not finish his question. Can you give him a chance to finish the question?
Quick one.
Hello, can you? Yes, I have a question for you, Edriss.
Okay.
Many years ago, you warned me, I think that was near the Weizmann, that one has to be very careful not to mix up the problem with solid boundaries for Euler, with those of infinite smoothness, periodic, etc. And now, given all the progress or partial progress that has been made in recent time, what is your feeling now?
I really don't know the answer to this question, Uriel. You gave me a question to think about. Okay, so I have to think about this question. I have to revisit it, and yes, I don't have an answer at the moment. A good question, and I have to really think more about it to see if it's really, anyway, that's my answer.
If I am allowed to come back and I just wanted to ask how important is the energy conservation of the schemes in this kind of problems? Because
I hear you. Yes, I think it is important. The conservation of the scheme is important, but the energy here is basically for the Euler, for the Voigt model, is not only the L2 norm, it's the L2 norm plus the alpha square gradient of U square. And at least numerically in the computation, let me go back here in the very first computations that we have seen, what happens? Voila. You see, when we do that, you see here is the sum is constant. Okay, this is the sum here, the first line, the horizontal line. Okay, and now you can see that the L2 norm is going down while the H1 norm is going up, namely the gradient are going up and this is going down such that the sum is remaining constant. At least this is based on the numerics. Okay.
Thanks very much.
Yeah.
Okay, hello. So you talked about convergence of this Euler-Voigt model to the Euler equation. But it seems like it was convergence for smooth solution. Do you have convergence for weak solution?
No, this is exactly what's my point. The point is, your very good question. The point was, and then let me come here, is just to okay, here is the result. So I'm assuming that the solution of Euler exists in the interval, then I can guarantee you that U alpha converges this interval. And because you converge here, therefore the energy should converge to the energy, namely this. This is the result that we have, that this plus this is less than that. So when alpha goes to 0, this sum is going to 0. In particular, the energy converges to the energy. Now, the whole idea is to show you, this is under the assumption that Euler is nice. If I can show you that this quantity does not go to 0, it means the gradient becoming so large and larger than the decay of alpha square. Therefore, I have, by contradiction, Euler cannot be smooth. So it's by contradiction in that sense.
Sorry, but independent of this result, do you have in general convergence of weak solutions?
Well, this is very good question, and I don't know, maybe you have been following the lectures by Helena Nussenzweig. I mean, I saw that she gave 3 lectures, whatever, and her lectures were about convex integration. In fact, prior to this machinery of convex integration and the work of even before Alexander, anyway, before the work of Edriss and Sikahidi, there was some work about showing some weak solutions which do not, which should be conserve the energy. In other words, let me go back. I retract. Before the convex integration machinery, there was a lot of attempts by the biggest, by the most senior people in the field, trying to establish existence of weak solution for Euler without success. So the notion of existence of weak solutions of Euler by the usual techniques of PDEs, like, oh, let's approximate the initial data, let us move, let's converge, we still do not know how to do it. The first time where people proved the existence of weak solutions for given initial data is using the convex integration. And in fact, the Cauchy problem, the first result about the Cauchy problem following the Edriss-Sikahidi machinery was a student of Sikahidi. His name is Emil Widman, which basically he proved the existence not only of one weak solution, but infinitely many weak solutions for the same initial data. So the only machinery that I'm familiar to establish weak solutions for Euler is the convex integration machinery, which is, as you have heard, at least from the lecture series by Helena Nussenzweig, that it is not really a PDE approach or a usual technique of PDEs in which you let some parameter go to 0 and then you have subsequences converging to different weak solutions. So the answer to your question is no, we don't know how to show that U alpha is converging to a weak solution for Euler equation. For Burgers, a different situation. You converge to a weak solution, but not necessarily beyond the shock, the entropy solution. And therefore, this is more criteria for establishing blow up rather than a machinery to converge for the weak solution, for physical weak solution.
I think the mechanism which actually introduces blow up, we can go, my view is if we go from viscous flow to inviscid flow to irrotational flow, and then the mechanism in viscous flow, there is a mechanism of viscosity which dampens everything, stabilizes the flow. And in inviscid flow, of course, that mechanism is missing, and obviously it will blow up easily. And then if we go to irrotational flow, the rotational element is missing, and so it will blow up easily. And then if we go to compressible flow, all these are incompressible, considering if we go to compressible flow, there is a compressibility effect which actually pumps the energy, and that increases the blow up. So, I mean, in my view, we are reducing the degrees of freedom reducing the degree of freedom as we go from viscous to inviscid to irrotation or potential flow. And that is why the blow-up is easier. And of course, when we go add the density variation, compressible flow, we are adding another degree of freedom. I mean, we are actually reducing the degree, more degree of freedom, and so it can blow up easily. See, if you have more degrees of freedom, then it can blow up easily.
So that was
that is the mechanism.
That was a comment. It was not a question.
Yeah, I understand, but I like the comment because it is remind me or to mention something. You know, let me go back into here, basically to your let's use mechanism. What happens is the following: when the energy is cascaded from say low wave numbers to high wave numbers, and if you have viscosity, it kills it. And now the point is that maybe in Navier-Stokes, the viscous dissipation is not strong enough to kill the amount of energy being transferred into the small scales. And now you ask the following question. In my equation, namely this Voigt model, okay, I have global existence in the Euler without viscosity. What happens to this cascade of energy? What's the mechanism that stops the singularity from happening? I think this is something which is interesting, and I had a scenario, and this is something that I'd like the physicists maybe to look into that. And this is all because of this particular term. This particular term, in some sense, inhibits the transfer of the energy. Notice that when the gradient are trying to become too large, the sum of them is constant. Therefore, this inhibits the gradient from becoming very large. Now, I might be able to stop sharing and go into another. Do I have time to show something else, or I don't?
Go ahead.
So let me just
wait,
close here. No, just bear with me here. Bear with me here. I have to go into some. Sorry, now you have to see all my secrets. And then, you know what? Let me go into here. Not the patient. Trying to see which Ramos. Very good. And this lecture I gave in Bangalore a few years ago, and now I would like to share with you, if you don't mind. Well, here it is. Okay, and now let me go into sharing screen again. Where do I do that? Share screen. Oh, share screen. Is it here?
Green
yes. And you can see statistical properties of Navier-Stokes Voigt model. This was 2020. And now it's about the same thing. So let me show you some picture, which is interesting. I hope I have it here. I'm going very quickly, trying to go to the computational. Okay, we did some computational for the Voigt model, but for the shell model, okay, the Sabra shell model. So maybe I should make this Control L. Okay, so this is the Sabra shell model, and then you add this Voigt model into it. Okay, and then what we have seen that this Voigt model, if you look for here, this is the one can show that I'm trying to see where is the picture I would like to show. Where is the energy? The structure. The structure function. So you can see that if this is, you look to the energy seemingly here around the wave number 1 over alpha, the spectrum becoming flat. Here around wave number 1 alpha, seemingly that this term is inhibit or slows the cascade of energy, so that basically it does not go too fast to the small scales to develop singularity. Before you go down, and viscosity will take care of that, but in the Navier-Stokes, the viscosity is not strong enough. Hyperviscous is strong enough, we'll do it. This one is in some sense is inhibit or slows or control the rate at which the energy is dissipated. And in fact, this is something which is, I asked physicists, this is simulation for the shell model to try to do it for the Voigt model. And you can see here that it's becoming very flat for different values of alpha. So this is a new mechanism of physics that this is introduces to the community that need to be investigated. That's basically what I'm saying. So I like your question in the sense that give me the chance to introduce that what viscosity does and what is this term is doing is in some sense inhibits the transfer of energy or slows down the transfer of energy such that it does not develop singularity in finite time, even though there is no viscosity. That's what, and this is something I would like physicists to comment on or to investigate. Now, whether this is of interest to the physicists or not, that's a different story.
Well, thank you very much, Edriss.
There is a question behind you, or we have to stop?
Probably next, we have photo session now. So thank you very much for interesting presentation, which was resonated with many of us. And good night. I mean, it's very late. How late it is now in Texas?
It is 11:10, so it's okay. Not too bad.
Then good evening. And
enjoy.
Thank you.
Bye-bye. Thank you very much for the invitation. Thank you for your questions. Appreciate it. Thank you.